Going on, guys, let's do this problem right here. Here this question is asking hot water flows through a 3 centimeter diameter thin walled copper pipe that is wrapped with 2 centimeter. So when they mention thin wall, this means there's no conduction due to this copper. So that's one thing we have to remember. And wrapped with 2 centimeters of insulation with thermal conductivity this value. The water temperature is 80 degrees Celsius and has a convection coefficient of this value with the pipe. The surrounding air is at 25 degrees Celsius with the convection coefficient this one. Now the question is asking to calculate the rate of heat transfer per unit length. Right, heat transfer rate per unit length. So here we are going to use Q dot, here we are trying to find Q dot over L. Now first of all we have to find Q dot, right? To find out Q dot we use this equation, that is delta T over R total. Now in order to do this one we have to find R total. Now here we have a cylindrical shaped pipe, right? So we have a pipe right here. Now we have to know what are the resistance we are going to have, and we know that there's no resistance due to this copper, but there's an insulation on top of this copper that is 2 centimeter. Now let's put the radius and diameters. So first we have this inner diameter that is 3 centimeter. So let's say DI, that is 3 centimeter, and they have mentioned that this is wrapped with 2 centimeters of insulation. So what's going to happen is here we are going to have 2 centimeter thickness around it, and if you imagine this is 2 centimeter, this is 2 centimeter, so totally we are going to have 3 plus 4 centimeter, so that's going to be 7 centimeter, right? So outer diameter is going to be 7 centimeter because this is, each side is going to be 2 centimeter and inner is 3 centimeter. So total we are going to have 7 centimeter. Now we have inner diameter, outer diameter. Now we can go ahead and find the resistance. Now let's look at the resistance. So if we draw the diagram for resistance, first inside we have water, right? So they have mentioned that's a convection. So this is inner is going to be a convection, and then due to this insulation we are going to have a conduction, and then we have outer convection, right? So these are the three resistance we are going to have. Now inner convection, to find out convection resistance we use this equation, that is 1 over H surface area. Now surface area for a pipe is going to be 2 phi RH, or you can use phi dl. Since we have the diameter we can use phi dl. So let's use phi dl right here, and this is going to be, so let's note D inside, right? And then we have conduction due to insulation. Now in cylindrical shape, if we have a conduction, to find the resistance we have to use this equation, that is ln radius 2 over radius 1. Here we have diameter over diameter 1 because the ratio for diameter and radius is going to be same, right? Now if you plug radius and diameter you will get the same ratio, so we can put diameter. So this is going to be d2 over d1 over 2 phi kl, right? So 2 phi kl, and then the next one, outer convection. Again we are going to have heat transfer coefficient phi d2 d outside, let's put d outside L. Now heat transfer coefficient is going to be different for inside and outside. Here they have given for inside this is 35 and outside this is 20. So these are the values we are going to plug. Now let's go ahead and substitute all the values, but here when we plug for diameter we have to plug this one in meter because that's the SI unit, right? So if we convert this one into meter, this is going to become 0.03, right? 0.03, and this is going to become 0.07 meter. Now let's go ahead and plug these values. First we are going to have 1 over inner convection, that is heat transfer coefficient, that is 35 watts per meter square Kelvin or degree Celsius, then 5 times D1. Now D1, D inside, that is 0.03 meter, so 0.03 right here, and we don't have the length, but in the question they have mentioned this is per unit length, so we can take unit length as length, like we can take L is 1 meter, so we can substitute 1 right here, right? Now this is going to be lambda. The next one is going to be, since they are in series, we can add them directly, so let's add them directly. This is going to be lambda d2 over d1. d2 is going to be outer diameter. Outer diameter is 0.07 and inner diameter, that is 0.03 over 2π. Thermal conductivity of this insulation is 0.05, so this is going to be 0.05 times the unit length, that's 1, plus 1 over h is h outside, that's going to be 20, and then multiply by 5 times diameter outside, that is 0.07 times the length, that's 1. Now if you calculate this one, you should get 0.30315 plus 2.69703 plus 0.22736, and that's going to give you 3.2276 degrees Celsius per watts, right? Now we have this information. Now all you have to do is plug it in this equation, and here we are going to have T infinity. So which one is hot? Inner is hot, right? So this is going to go from inner to outer, so T infinity inside minus T infinity outside divided by R total, that's going to be 3.2276 degrees Celsius per watts. If you calculate this one, you should get 17.0, right, around approximately 17.0. This is watts, and here the question is asking to find out per unit length, so this means if we have to divide this one by 1, so Q dot over L is going to be just 17.0 watts per meter, and that's going to be the final answer. I hope this helps. Thanks for watching.